Okay, so last time we were discussing limits and continuity. Some of the limits that we discussed were infinite limits. That is, limits that in which we usually have x approach a value of x that happens to be a vertical asymptote. And well, depending on the orientation given by the function. Okay, guys, let's get started. All right. So depending on the function, well, we got a positive infinity or a negative infinity depending on the type of function. That was infinite limits. Today we're going to look at limits at infinity, which is something different. And this limit at infinity is, well, what's the limit when x approaches infinity? That is, in a way, we are going to, well, not really plug in a value of infinity, because ultimately, well, that's not a number, that's just an idea of something that never ends. Okay, so this is what we got from the previous section. So like limit x approaching 3 from the right for this given function. Well, just briefly, this one has a 1, 2, 3 vertical asymptote at x equals to 3. And let's draw that. That means, well, we are going to have this function right here, this graph, but in this case approaching 3 from the right. Essentially we're looking, it's going all the way to positive infinity. Okay? Well, those were infinite limits whose result are positive infinity or negative infinity. Now, let's look at the other kind of limits, that is limits at infinity. So we're going to consider this function right here, f of x equals x squared minus 1 over x squared plus 1. Well, so in this case we want to know what's the value of the function for relatively large values of x, you know. So I have a table over here. So whenever x equals 0, evaluated, you should get 1. So I'm not going to do the calculations because, well, that's going to take forever. I'm just going to give you the table. Or even better, it would be easier to just look at the graph. I mean, you can see it from the table, but we're going to get to see this from the graph. So this is the graph of f of x. X squared minus 1 over x squared plus 1. Alright? Well, now in this case, we want to find out what's the limit as x becomes large. Infinity. Well, what is the y value that the function is apparently being hit to? And in this case, it's this horizontal asymptote. Well, this would be a really big connection between limits and something you studied back in pre-calculus, horizontal asymptotes. Those horizontal asymptotes actually will turn out being the values of x for which the function takes x values really large. Well, how large? Infinity. All right. So that's one example. That's an example on a short example on a graph. Well, let's look at a definition. So if we have a function f defined on some interval a to infinity, that could be 5 to infinity, 1 to infinity, 0 to infinity. Well, that's going to depend on the domain of the function. Well, so limit of f of x as x approaches infinity, it's going to be a number L, and that's going to be the value of that horizontal asymptote connecting with the pre-calculus stuff. And on the other hand, well, we have the idea of having that x to be sufficiently small. How small? Really small in the direction of negative infinity. This is, okay, that's actually means very small, negative infinity, and really big, positive infinity. Alright? So in this case, we're going to check those limits on both sides of the infinity. So for example, let me go back to this example right here. So What's the limit again? X approaching infinity. Isn't it the limit? So we said it was approaching 1. But we also can look at the graph in the other direction, going towards a negative infinity. That's limit f of x, x approaches negative infinity, and the limit is also 1. Okay? However, in this case, we're not necessarily determining whether these two values are coincident. It doesn't matter. In fact, it will be possible that we can have two horizontal asymptotes, and we will discuss that a little later today. All right. So let's have a look at this piece of information. So what about that symbol, that infinity symbol? So this infinity symbol, of course, it's not a number. It's not like we do operations with infinity. Well, we sort of do, but there will be one case in which the operation is not going to work well. Again, infinity is just an idea of something that never ends, something really, really big and keeps increasing, never ends. Okay, so let's look at these statements right here. So when you have a really, really big number, add a number like 2, like 3, well, it's still infinity. When you have a number, subtract infinity, well, basically that's negative infinity, or infinity times a number, well, it's still even bigger, but it's just infinity. We can add infinities and multiply infinities. No, this is not going to be 2 times infinity. This is not going to be infinity squared. And the reason for this is because we don't know which infinity is bigger than the other. And that's the issue when it comes to subtracting infinities. So you might think that infinity minus infinity would be 0, right? Because 5 minus 5 equals 0. 7 minus 7 equals 0. Unfortunately, this is not the case with infinities, because again, we don't have an idea of which infinity is bigger than the other. So all these weird statements right here are called indeterminate forms, and this is something that we will deal with later in when we get to limits. I believe it's chapter 4 or chapter 3, you're using the L'Hopital's rule, but that's coming later. All right, well, this is the connection between the precalculus and the calculus. So the line y equals to b is a horizontal asymptote. If either or both of these are true, that is the limit as x approaches negative infinity for f of x equals to b, or limit x approaches infinity as for f of x equals to b. And that's in this case, it's true for both. For the example that we did before, we got the same limit in both directions, positive infinity and negative infinity. There are cases in which going to different infinities might give us a different y value, or the limit would be a different value. You'll see those cases in a second. All right, what's next? Let's have a look at some of the functions, some of the elementary functions, and find the limits at infinity, which, in other words, all we're doing is to find the location or the equation of that horizontal asymptote. Well, what do we have over here? Limit of x cubed. Well, x cubed, does the function x cubed have any asymptotes? I mean, this is the graph of x cubed. It doesn't have any asymptote, does it? Well, so basically infinity cubed, where is that going to go? How big is it going to be? Just infinity. All right. Okay, what about cosine? Okay, be careful with some of the trigonometric functions. So cosine, which happens to look like this, well, that's the same graph forever, right? It just oscillates between -1 and 1. However, in this case, what would be the limit for cosine at x equals when x approaches infinity? Any ideas on?
Would it just be like a range between 1 and -1?
It's just, well, so we would say it's dne, because this function just bounces back and forth between -1 and 1, so dne due to oscillations between -1 and 1, which is actually the range of the cosine function, right? Let's have a look at the function e to the x as x goes to -infinity. All right, let's see. So it would be a good idea to draw the graph of the exponential function to help us see what we get. All right, the following graph, this is the usual graph that you get to see when you're looking at the exponential function. All right, but I claim something's missing in that picture. Something is missing in the textbooks pictures when they present us with the graph of the exponential function. What's missing? Any ideas of what's missing in the picture? Yes. A horizontal asymptote, which is actually the x-axis, and the reason why they usually miss this information is because this asymptote overlaps with the x-axis, so that's why they don't show it. Or maybe on the text they specify, oh, by the way, the x-axis itself is a horizontal asymptote. Now, let's have a look at the limit e to the x at x approaches infinity. What would be that limit? It's approaching 0 because we're going towards a -infinity. That is, we're doing this. Alright? And we are going to get close to 0, but never actually touch that 0. We're getting asymptotically close to 0. So that will be 0. Let's look at another one. So limit 1 over x. Let's draw the graph of 1 over x. And we know the graph for 1 over x looks like this. Now, what's the limit as x goes to positive infinity? 0. Now, another piece of information that we usually miss, again, is also this horizontal asymptote right here. Mostly we'll look at this vertical asymptote, but there's also a horizontal asymptote over there. And well, yes, in this case, 0. So that's by the graphing approach. Now, let's think of infinity as a number. Well, it's really big. What happens when you divide 1 by infinity? What should we get? Or any number by infinity? 0, right? Well, to relate to this, usually my approach is, well, you have a pizza, you share with a friend, you only get half of the pizza. You share with other 7 friends, you just get 1/4 of the pizza. You share with 99 people, you just get 1/100 of the pizza. You share the pizza with an infinite number of people, what do you get? Nothing, right? 0. All right, e to the x. Let's go back to the e to the x. I'm not going to draw the graph again. We already have it here. What's the limit as x goes to infinity? Is it going to go to 0 just like going back to -infinity? Where is it going to go then? Infinity. Okay, ln of x. Let's see what about ln of x. Let's draw the graph. So this ln x has a vertical asymptote at the y-axis, and the graph looks like this. Well, For large values of infinity, this one definitely is going to go to infinity. All right? Number 7, 1 over x, x going to negative infinity. Let's use this same graph right here. Where is this going to go to? 0 again, right? 0. And what about e to the negative x? Alright, e to the negative x as it goes to negative infinity. Alright? So, number 1. What about e to the x in the denominator? Alright? Well, no, not this. Well, let's think of the algebraic way to do this, and then I'm going to go with the graphic approach. So this would be basically e to the negative infinity, which will really turn into positive infinity. But what's e to the big number? Infinity. What about the graph approach? Well, for the graph, when we have the exponential function with a negative exponent, recall that this describes a decay. And don't forget the horizontal asymptote. Now, so in this case, we want to approach not positive infinity, but negative infinity. Where is this going to? Isn't it all the way to positive infinity? Alright. And the last example. Alright, sine x over x squared. Okay. What's going to happen with the sine at infinity or negative infinity? Doesn't matter. So, in a similar case as cosine did, what happened with cosine? It went oscillating between negative 1 and 1, right? So, okay. So let's look at each individual case. So sine oscillates negative 1 and 1 over big number, and from here we can further describe two different cases. Number 1, the case in which negative 1 over big and 1 over big. Alright, so divide a number over a big number over infinity, isn't it 0? And same for the negative, you should get 0. So this limit is 0 regardless, despite of the oscillation and okay? Now, the question is, can a graph have two horizontal asymptotes? Yes, it's possible. Can any of you think of a function that has two horizontal asymptotes? Sine? Well, the sine function doesn't have horizontal asymptotes, but you're getting there. It's related to the trigonometric, yes?
I felt like y equals 1, y equals 2.
Oh, well, those are asymptotes, but I mean a function that has two asymptotes.
The inverse graph of x cubed.
The inverse of x cubed. Oh, I see. Okay. I think this is really good to start well. So when you have like y equals x cubed, this looks like this. And x equals to, y equals, do you mean the cube root of x?
Yes.
Which looks like this, right? However, these actually go to negative infinity, because take the cube root of a big number, it keeps increasing without bound, and these horizontal asymptotes are actually the bounds. However, this is a good example because, well, the function I'm looking for has this shape, in fact. The inverse tangent function. The inverse tangent, you got it. Y equals arctan x. Well, so the function y equals arctan x, which looks similar to the y equals cube root of x. However, we have horizontal asymptotes. In this case, negative pi over 2 and pi over 2. Well, where is this coming from anyway? So this comes from the fact that the function y equals tangent has the following graph. It has this graph right here, vertical asymptote, graph here, vertical asymptote, and repeats forever. Now, clearly, the inverse tangent function, it's not a one-to-one function, and in order to define an inverse function, we have to have a one-to-one function. How do we define a one-to-one function? You want to remember from the beginning of the semester that a function is one-to-one, and from the graphic approach, if it passes the horizontal line test. And in this case, the horizontal line test only actually crosses, from this picture, crosses 3 times. So recall, this will have infinitely many graphs, because it's a periodic graph, so this function will fail the horizontal line test. However, if we restrict the domain of the function, which is one of the tricks that we did back then, if we only take this part of the graph and its asymptotes, that would become an invertible function. Well, when we invert the function, it's going to look like this. These x's right here, which are negative pi over 2 and pi over 2, these are the vertical asymptotes. When we invert the function, these vertical asymptotes become horizontal asymptotes, right? And yes, this is an example of a function that contains 2 horizontal asymptotes. Thank you. All right. Let's see. Whenever we have rational functions, we will now get to compute limits algebraically, but in this case, evaluating those limits at infinity. So, the trick here that whenever you have a limit of a quotient between 2 polynomials, yes, this is a rational. This is the definition of a rational function, quotient of the polynomials, whether negative infinity or at positive infinity, doesn't matter. The trick is the same. What we're going to do is divide out numerator, divide both the numerator and the denominator by the highest power that you see in the denominator. Alright? Later I will give you some shortcuts, but in the meantime, at least for what it will be this first part of the course and whatever will be for the first quizzes and exam, we will have to do this actually the long way. So let's look at an example that illustrates this idea. Alright, so let's evaluate the following limits. So to evaluate the limit 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So number 1, we need to identify the highest power of x in the denominator. What is it? X squared, right? So this is what we have to do. Limit at x approaches infinity of 3x squared over x squared minus x over x squared minus 2 over x squared, and 5x squared over x squared minus 4x over x squared plus 1 over x squared. Okay? And let me change this. Oh, come on, I don't want the whole thing. Now, let's simplify this. So this will be, okay, x squares cancel here. That's going to be a limit of 3 minus x over x squared, which is 1 over x. And, well, there's nothing to reduce here. 5 minus x over x squared, that's 4 over x minus 1 over x squared. As x approaches infinity. Now, here is where we will compute these individual limits. Question?
Is it plus or minus 1 over x squared?
Which one? Oh, this one's supposed to be plus. Thank you. Plus, plus. I don't know where did I get the minuses. Thank you. All right. right, let's evaluate these limits. So the quantity 1 over x. So no need to like show the graph, the graphical analysis. We already did that. So essentially, we have 1 over big number, 1 over infinity. Where is this going to go to?
It's going to 0.
0, right? Again, this is also, what about this one? And that's it. What are the terms that survive?
3 and 5.
3 over 5. That's our limit. Alright. Well, that's the limit at infinity, and that also, graphically, that happens to be the equation of the horizontal asymptote. Let's look at another example. What do we have? Limit at as x approaches negative infinity of the quantity to x cubed minus 5 over 3x squared plus x plus 2. Alright? Well, so number 1, we need to identify the highest power in the denominator. What's that 1 power? X squared. So we need to divide all terms in the numerator and the denominator by that highest power of x. Alright, so let's see. So that's a limit 2x cubed minus minus 5 divided by x squared and divide by 3x squared plus x plus 2 x squared limit x approaching negative infinity. Now let's simplify this the same way we did it before. Okay, what's x cubed over x squared? So that 2x and negative 5 over x squared divided by, okay, cancel the x squared, that's 3 plus 1 over x plus 2 over x squared. Okay? Alright, now here is the thing, careful. Where is this going to go, first of all? 0, right? Because that's a number being divided by a really big number, so we get small. How small? Well, 0. What about this one? 0. What about this one? 0? Okay. Now check this one out. I'm going to use a different color for this one. Where is this one going to go? Negative infinity. So this is going to blow the whole thing up to negative infinity. Okay? Alright. The next example is actually a great example in which we will incorporate a number of definitions and their implications in, well, the result that we are going to obtain. So even though, yes, I know, this is not a rational function because this function doesn't meet the requisites to be a rational function. This one is not polynomial over polynomial. It's actually radical over polynomial. It's not considered a rational function. It's just a quotient function. All right. So this is what we're going to do. Well, let's express this as the limit. Limit square root up to x squared plus 1 as divided by 3x minus 5 as x approaches. Okay, let's do infinity. Okay, let's do infinity. Okay, so number 1, let's see. If we do the direct substitution the same way we did it before, Well, this is kind of weird to do again because we really don't do arithmetics with infinity like the same way we do 2 times 5 minus 3. Okay, that's a 10 minus 3 equals to 7. No, we don't do the same with infinity, but in a way we will have to do it just to have an idea of what we're going to get. So, in the numerator, so that's the square root of 2 times infinity squared. Plus 1, well, infinity squared, it's still bigger, it's still infinity, and then that times 2, it's still infinity, and then add 1 to that already big number, well, it's still infinity. Take the square root of that infinity, we don't know how big it is, let's just say it's infinity. And well, 3 times infinity, well, even more infinity. Subtract 5 to that infinity, is that minus 5 going to do any harm to the infinity? So it's still infinity. Alright, this is another one of those indeterminate forms. In the previous sections, we discussed how the 0 over 0 is one of the determinate indeterminate forms. Infinity over infinity is one of those indeterminate forms. Alright, so, and let me go back to those indeterminate forms here. So in this case, we discussed them over here. Okay, yeah, that's the one that we're discussing. In chapter 3 or chapter 4, we're going to look at infinity minus infinity, infinity to the 0, 0 times infinity, and 1 to the infinity. Those are going to be weird indeterminate forms. Don't worry, we're going to discuss those in detail. So, okay, what about this limit? Well, so we are supposed to do algebra on this limit, on this expression, in the same way that we did in the previous section. Factoring out the difference of squares or the sum of the or difference of squares with cube. Factoring the trinomial, divide out a factor. What else did we do? Rationalizing denominators maybe, or what else did we do here? Expanding a binomial or trinomial, simplifying the complex rational expression. Well, I don't see anything of this in this expression. So what are we going to do? Well, I'm going to factor, but wait a minute. We don't have any greatest common factors over here, do we? Do you see any greatest common factors here? Do we have a GCF over here? No, but we're gonna make it happen. Check this out. So, limit x approaches infinity of the square root of, I'm going to factor out an x squared inside of the radical. But wait a minute, it's only the first term that has the x squared. Well, yes, that's x squared times 2 plus what quantity multiplied with x squared would give me back the 1? 1 over x squared. Alright? That's one of the tricks. I'm going to do the same trick in the denominator. Yes, I'm going to factor out an x even though it's not common on both terms. But we're going to make it happen. Factor out the x and then use the trick 3 minus 5 over x. Alright? If you distribute this back, you should get back to the original problem. This trick right here, you may not have seen it in your algebra class. So typically your algebra class is factor out GCFs and all the different methods. You may not have seen this before. However, it's important to get used to this weird trick because we're going to use it a lot throughout the semester. You're going to use it a lot in calculus too. I'm using it a lot when computing integrals that give arc-length surface areas to simplify a lot of the work. But right now, don't worry about those. You will worry about those when you get to Calc 2. In the meantime, let's just take advantage of these weird tricks. So number 1. We have the radical of a product. We can use the product rules for radicals. And in fact, we happen to have a perfect square. What's the square root of x squared? Just x? something you might remember from the radical theory. Whenever you have the square root of x squared, this is the absolute value of x. And I think we discussed this a couple of times over here as well in this class. And we will have to do that. So, this means, okay, we're going to obtain limit x approaches infinity, absolute value of x, square root of 2 plus 1 over x squared over x 3 minus 5 over x. Okay, so in this case, how can I go about this? Well, number one, this absolute value, recall that this absolute value will be square root of x squared, which is the absolute value of x. So depending on the direction that we go, this can be negative x for values of x less than 0, that is for negative values of x, or it can be x for positive values of x. Alright, now some of you say, I heard you say, okay, it's x. Yes, it's x in this case. Ultimately, it's just x. And that's because, well, which direction are we going in with the limit? Are we going in the positive direction or are we going in the negative direction? Because we're going in the positive direction, check this out. I'm gonna go positive direction. We're gonna use the positive version of the piecewise function, and we will replace this absolute value of x with simply limit with x. Okay, let me also highlight this part. So x square root of 2 minus 1 over x squared over x 3 minus 5 over x as x approaches infinity, and only then we would be able to divide out this x over x, which is the troublesome ratio here. By troublesome ratio here, what do I mean? Well, it's that ratio that is causing this trouble here, the infinity over infinity. We got rid of that garbage. Okay, we're good. We're safe. We're safe. That means limit square root of 2 minus 1 over x squared over 3 minus 5 over x as x approaches infinity. Well, let's analyze every single term. Where is this going to go to?
Wait, so sorry. Just disregard the absolute value again?
Oh, because in this case, since we're going in the positive to the positive infinity, so x is positive, so that turns into x. I'm going to discuss the other side in a second. So where is this going to go to? 0. Where is that going to go to? 0. Well, so limit x approaches infinity. No more limit symbol because we're already computing the limit, so that the square root of 2 minus 0 over 3 minus 0, that's simply the square root of 2 over 3. Okay, so this function has a horizontal asymptote at root of 2 over 3. Let's analyze the other case. Oh, that's fine. How about we evaluate the limit x approaches but negative infinity this time? Well, I'm not going to start from the original limit. Well, let me just write it down. 2x squared plus 1 over 3x minus 5. I'm going to jump to this expression right here, the part where we factored out this x. Limit absolute value of x square root 2 plus 1 over x squared over 3 minus 5 over x. But in this case, we're going to negative infinity. So now, this absolute value factor will have a totally different meaning. And the reason for this is because, check this out, we're going towards negative infinity. We're looking at negative values of x. Because of that, we're going to take the piece of the piecewise function that it's negative because x is going in the negative direction. You see where I'm going with this? Are you guys following me here? Okay, so that means that this absolute value of x, it's going to be limit of negative x, negative x to plus 1 over x squared over 3 minus 5 over x as x approaches negative infinity. Okay, I'm going to keep highlighting this with red just so you can see what's the critical part that it's changing here due to this connection with the definition with the absolute value. Oh, I forgot the x, right? I forgot the x right here. I also forgot the x right here, okay? All right, so what do we have? So this is going to be, well, we may now cancel the troublesome ratio, x over x. That's what's causing the trouble of infinity over infinity, and we shouldn't get any indeterminate forms up to this point. We cleaned up this garbage. Let's just go ahead and evaluate the limit. We're safe now. Algebra to the rescue, right?
Do you not have like a negative value still there? Like
Yes, I was changing colors. Yes, that's a negative. So this will be, again, goes to 0, goes to 0. Essentially the same result as before, but a negative. All right. So yes, this is one example, another example of a function that has two horizontal asymptotes. I guess the most straightforward one was the one that was mentioned by one of you, which is the arctan function. All right. Well, this is pretty much what I have for today. But let me make up another example that I think it's going to be that it's something that you will see on the homework. You may see it on a quiz. You may see it on the exam. So let's see. What about this limit? Limit e to the 4x minus e to the negative 4x over e to the 4x plus e to the negative 4x as x approaches infinity. Whoa, this is going to be interesting. Well, number one, so the approach will be very similar. So in the previous example, we were supposed to look at the highest power of x that you see in the denominator. However, these are not polynomials anymore, are they? However, well, we may not have, a highest power of x because of a polynomial. However, we have a highest power of an exponential function. So let's observe those powers. So we have a power for x, power 4x, and we have a power negative 4x and negative 4x. The question is, which of those two powers is the highest of both? Is 4x greater than negative 4x or vice versa? Well, the positive one should be greater, right? So that means in this case, we will divide all terms. Hold on. Yes. Oh, by the way, e to the negative infinity, e to the negative infinity, this is going to give us positive, the infinity over infinity indeterminate form. So that's limit e to the 4x minus e to the negative 4x divided by e to the 4x, e to the 4x, and then divide that by e to the 4x plus e to the negative 4x divided by e to the 4x, e to the 4x. And in this case, as x approaches infinity. Alright? Okay, what's going to happen here? Well, number one, we should be able to divide these two out. No big deal, because they're the same factor, numerator and denominator. And careful with simplifying the other exponential ratio. So number one, so far we're left with the following: limit of e to the 4x divided by itself, that's 1, minus what is e to the negative 4x divided by e to the 4x. Notice we have the same base, e. What do we do with the exponents when we divide the bases? So what is negative 4x minus 4x? Negative 8x. Okay, e to the negative 8x. Same in the denominator, 1, but plus e to the negative 8x. Whoops. As x approaches infinity. Alright, so to find these limits at infinity, I'm going to write these negative exponents with positive exponents. That's limit x approaches infinity. That's 1 minus 1 over e to the 8x over 1 plus 1 over e to the 8x. Well, in a very similar way, when we evaluate limits like 4 over x squared, well, that went to 0. But what about this limit? Where is this limit going to go? So, if let's say we're plugging the value of infinity. Infinity times 8, well, 8 infinities, it's still infinity. And then exponent e to the infinity, it's still going to make it bigger. So we divide by a big number. This is 0. This is also 0. And the terms that survive are 1 over 1, which is 1. Final answer. Alright? Question?
What's going to be on the test?
I believe it's up to this limit at infinity, what it's going to cover. That's a good question, because I was talking to the other Calc 1 instructors, and it turns out that we all fell behind. Because last Friday we were supposed to cover 2 sections, but it was too much to cover in 15 minutes. So I think that's my either the course coordinator or I will be sending emails during the weekend to see if anything is going the study guide, use your lecture notes, use your worksheets that you do, the resources to study from, also the homework that you do from web assignment. So you are supposed to write it out on paper and submit a PDF file or picture. That's also a good resource for typical examples. Yes.
Well, first of all, I guess, can you see that last video? How are we supposed to submit the homework assignments? Because everyone just writing them out.
Okay, you write them out and submit it through Rachel. Either a picture or a picture.
Great, okay. Well, did you say there was a study guide somewhere?
No, there's no study guide. But the study guide is all the resources that you have.
Okay, and what's the part of the section number that's going to be on the test?
This is section 2.6.
So up to section 2.6?
Up to section 2.6, but I need to figure that out because, like I mentioned, pretty much all instructors fell a little behind, so things might change. So I will be either the course coordinator or myself will be communicating during the weekend to inform about those changes.
Okay, so by Sunday night we'll know.
Or even later today.
Okay, so it might be higher than 2.6 or lower than 2.6?
2.6 and below.
And below.
So for now, but I still need to figure it out. I just sent an email to Candace later today.
Okay, but I'm saying it could be another lesson from Monday.
No, because the exam is on Wednesday, and we're learning something on Monday. It's too close to the exam, so that's going to be unfair. Alright. Yes. it's in my YouTube channel, but I posted the link on Canvas. There is a module called lecture recording or so, and they're organized by date. Yes, and some of the calculus topics, exactly. Question? No, we're going to move on to the topics. I guess the starting would be on Tuesday the 5th. Because really 15 minutes wouldn't be enough to like review the whole thing that we have done for the entire month, right? Usually these exams are like 6 or 7 pages. So with like multiple parts on questions. So that's a good question. I wouldn't be able to answer that question because it varies, it varies from exam to exam, from class to class, right? So depending on the complexity of the topics, some topics go with exercises that take forever to solve, while